Welcome everyone. Today we're going to explore the essentials of API 610, focusing on centrifugal pumps. This slide serves as our introduction, highlighting the purpose, the key formula for power calculation, and the main application criteria. We'll cover how these standards ensure reliability and mechanical integrity in critical industries like petroleum, petrochemical, and gas. We'll also look at the design and testing requirements that help maintain efficiency, vibration limits, and proper sealing. So, let's dive in and get a clear overview of what API 610 entails for centrifugal pump design and operation. Let's take a closer look at API 617, which focuses on centrifugal compressors. The main goal here is to set standards for the design, performance, and testing of these compressors, especially when they operate continuously in demanding environments like refineries, LNG facilities, and chemical plants. Now, an important aspect is the work, measured in kilojoules per kilogram. There's a specific formula that helps us calculate this work, which considers the compressor's efficiency and the thermodynamic properties involved. It involves parameters like the ratio of pressures, the gas constant, and the inlet temperature. For example, if we plug in some typical values, say, a specific heat ratio of 1.4, a gas constant of 8.314, an inlet temperature of 300 Kelvin, and a pressure ratio of 3, we get approximately 68 kilojoules per kilogram of work. This helps in designing and optimizing compressor performance. Moving on to applications, API 617 emphasizes key factors such as rotor stability, ensuring the rotor stays balanced and operates smoothly. Critical speed should be at least 10% above the operating speed to prevent resonance issues. Gas seals, which are covered under API 692, are vital for preventing leaks. Performance testing is essential to verify that the compressor meets expected standards, and vibration levels need to stay below 4.5 millimeters per second to avoid damage. Lastly, a run test lasting at least 1 hour is required to ensure reliable operation over time. Understanding these points helps us ensure that centrifugal compressors are safe, efficient, and reliable in their critical roles across various industries. Let's take a closer look at API 672, which focuses on packaged air compressor units. The main goal here is to set clear minimum requirements for integrally geared packaged air compressors, especially those used in plant and instrument air systems. These standards help ensure reliability, efficiency, and safety across different applications. Now, a key point is understanding how to calculate the air power needed. The formula we use is air power in kilowatts, which equals the flow rate multiplied by the pressure differential, divided by 102 times the efficiency. To put it simply, if you know the flow and pressure, you can determine the power required for the compressor, making it easier to select the right equipment. For example, if we have a flow of 0.5 cubic meters per second and a pressure difference of 8 bar, with an efficiency of 85%, plugging those into the formula gives us approximately 46 kilowatts of power needed. This calculation helps us size the compressor properly and avoid under- or over-specifying equipment. The applications of these standards are quite broad. They include seamless package integration, noise levels kept below 85 decibels, vibration limits under 4.5 millimeters per second, and motor protection rated at IP55. Additionally, cooling and control systems need to be checked thoroughly, and the compressor must undergo a run test of at least 1 hour to verify performance and reliability. All these points tie back to our overall goal, ensuring that the packaged air compressor units are efficient, durable, and suitable for their intended industrial environments. Let's take a closer look at API 670, which focuses on machinery protection systems. The main purpose here is to set clear standards for monitoring critical parameters like vibration, position, and temperature. These measurements are essential because they help us protect rotating equipment from mechanical failures that could lead to costly downtime or damage. For example, the system is designed to trip the equipment if vibration levels exceed 9 millimeters per second RMS, or if axial displacement goes beyond 0.25 millimeters. These thresholds are carefully established to ensure early detection of potential issues. In terms of applications, API 670 encourages the use of dual sensors for redundancy, which increases reliability. It also supports redundant logic configurations, alarm verification processes, and automatic trip functions to ensure safety is maintained at all times. Trend monitoring is another key aspect, allowing us to track changes over time and predict failures before they happen. And importantly, API 670 integrates seamlessly with distributed control systems, or DCS, enabling centralized monitoring and control. Overall, this standard helps us implement robust machinery protection, ensuring safe, reliable, and efficient operations across our facilities. Let's take a closer look at API RP 686, which focuses on machinery installation and alignment. The main goal here is to establish best practices that help ensure our rotating machinery operates reliably over the long term. This includes proper installation, precise alignment, and correct startup procedures. When we talk about tolerance limits, we're referring to the acceptable variations that won't impact performance. For example, an offset of less than or equal to 0.05 millimeters, soft foot of 0.03 millimeters or less, and piping strain not exceeding 700 newtons. Keeping within these limits is crucial for minimizing stress and wear on the equipment. Now, the applications of these practices are quite broad. They include hot alignment correction, which allows us to adjust for thermal expansion, grouting checks to ensure proper support, coupling tolerance measurements, soft foot tests to detect misalignments, base plate leveling to achieve a stable foundation, and maintaining an alignment record sheet for documentation and future reference. All these points tie back to our overall theme of ensuring machinery reliability and efficiency. By adhering to these recommended practices, we can prevent issues before they arise, extend the lifespan of our equipment, and optimize maintenance strategies. Let's take a closer look at ASME B31.3, which focuses on process piping. The main purpose of this standard is to govern the design, fabrication, examination, and testing of piping systems specifically used in chemical and petroleum plants. These industries require rigorous standards to ensure safety and reliability. One key concept here is the test pressure. According to the formula, the test pressure should be 1.5 times the design pressure. For example, if the design pressure is 10 bar, then the test pressure would be 15 bar. This ensures that the piping system can handle pressures beyond its normal operating conditions, providing a safety margin. Now, let's talk about some of the critical applications of this standard. It covers welding procedure control, which is essential to ensure weld quality. It also includes non-destructive testing, NDT inspection, to detect any flaws without damaging the pipe. Hydrotesting at 1.5 times the design pressure is a standard practice to verify the integrity of the system before commissioning. Additionally, the standard emphasizes stress analysis to prevent failure under operational loads, nozzle load checks to ensure attachments don't cause stress concentrations, and material traceability to ensure all materials used meet specified standards. Overall, ASME B31.3 ties into the broader theme of safety and quality assurance in process piping systems, helping us maintain reliable and secure plant operations. Now, let's take a closer look at ASME Section VIII Div 1, which deals specifically with pressure vessels. The main purpose here is to establish clear requirements for their design, fabrication, inspection, and testing, ensuring safety and reliability in process industries. One of the key elements is the formula used to determine the wall thickness of a pressure vessel. It's given by thickness in millimeters equals P times R divided by S times E minus 0.6 times P. This formula helps us calculate the minimum thickness needed to withstand the internal pressure safely. For example, if we plug in some typical values, say P equals 10, R is 1000, S is 120, and E is 0.85, we get a thickness of about 10 millimeters. It's a practical way to ensure the vessel can handle the pressures involved without over-designing or under-designing. Moving on to applications, this standard influences many aspects of pressure vessel design and documentation. We're talking about the nameplate design, joint efficiency, and hydrotest requirements, often set at 1.3 times the design pressure, to verify the vessel's integrity. It also covers material certifications, corrosion allowances, and maintaining thorough inspection records. All these components are interconnected, forming a comprehensive approach to safety and compliance in pressure vessel design and operation. Remember, understanding these requirements is crucial for ensuring that the vessels we work with are both safe and efficient throughout their service life. Let's talk about project execution and leadership. The core idea here is that success in project execution comes from a combination of experience and leadership ability. Specifically, we can think of it as a formula. Experience in various project phases multiplied by proven ability to lead and coordinate equals successful execution. For example, this might involve planning, scheduling, conducting, and coordinating engineering work. It also means taking on a lead technical role, mentoring junior engineers, and driving the front-end engineering design, or FEED, through to actual execution. But beyond just individual contributions, engineers need to manage work streams and guide their teams through the entire design and execution process. Ultimately, project success depends on three key factors: team synergy, technical control, and leadership vision. When these elements come together, they create a strong foundation for delivering successful projects. This ties back to our overall theme. Effective leadership and collaboration are essential for turning plans into reality and achieving project excellence.